Good morning. A few announcements before we get started. Exam 1 will be next Friday. So in order to prepare most efficiently, please look at Exam 1 from 2015 and 2016 so you get a feel for the level of questions that will be asked. Also, homework 1, which kind of covered the first week and maybe the first day of this week, and homework 2 should be looked at before the exam and done. When you do them, I know I supplied the solution keys at the same time, but please don't look at them until you've given it, your full effort. Sam and Mickey will be going over the questions that you may still have on the homework next week in office hours. But since my office hours are the same day as the exam, what I'm going to do instead of my office hour next week is I'll do a video office hour, so you can send me your questions between now and the end of the day Tuesday. Then I'll record a response on Wednesday and put that online Wednesday instead of my office hour next week. So you can ask me anything. I'll choose the questions that I think will help you the most for the exam. Questions about the homework should in general be directed toward Mickey and Sam's office hours next week, because they'll be prepared to go over the exam problems. The homework problems. Okay, thank you for returning to class after Wednesday's lecture. I know it was not the most pleasant topic, or maybe for some of you who are probabilistically inclined, it was. But that was the last day of the mechanics of step growth polymerization, and today we're going to switch to chain growth polymerization. So what was typical in step growth polymerization is that we had these AB type monomers or AABB type monomers that ended up giving us products that looked something like my favorite polymer and yours, nylon 6,6. And what are some characteristics of this polymer? It has these motifs that have these C double bond O bonds along the backbone, and also atoms in the backbone that aren't carbon. So they're called heteroatoms. They're atoms that aren't carbon or hydrogen. And this is really a hallmark of products or of polymers that are produced by step growth polymerization. You have this carbonyl and then this heteroatom next to the carbonyl, and this is just an artifact of the fact that you're starting with an acid or an acid chloride plus an amine or an alcohol to give you either an amide, as I've drawn, or an ester, which has the NH replaced with an O. So polyamides like nylon and polyesters are generally grown by step growth polymerization. Not always, but it's this is at least some forensic evidence that it may have been produced by a step growth polymerization. In contrast, we have polymers like polymers that have only carbon atoms in the backbone. And this is called a polyolefin. And it has substituents, which are the things that substitute for hydrogen atoms along the backbone. And they can be a bunch of different things. And they are all derived from a vinyl monomer, which is a monomer with a double bond and the X group here. And you can make these structures by radical polymerization, which we'll talk about today, which is polymerization mediated by unpaired electrons that travel down the chain and add a new monomer as they go, or they can be made by ionic polymerizations like anionic or cationic polymerizations. While these types of polymers can sometimes be made by chain growth mechanisms, polyolefins are always produced by chain growth mechanisms. And so if X, for example, is a benzene ring, it's polystyrene. If it's chlorine, it's polyvinyl chloride. If it's methyl, so just CH3, it's polypropylene, and so on. And how does this work? So for radical polymerizations, I'm going to show you the general flow here, and then we'll look at each step in more detail. We have an initiator. And the initiator has a radical, which is an unpaired electron, which is a dot. Unpaired electron is a dot. Then we have some monomer, and we will use styrene. And what happens, and I'm never going to make you draw reaction arrows in this class, but if you're interested, this is where the electrons go. And also, if you're interested, a single-headed arrow indicates the movement of one electron, and a double-headed arrow indicates the motion of two electrons. Okay, so this is the initiation step. Then you end up with a product that has the initiator fragment on one end and then one added monomer, but because we always have to conserve our radicals, we still have a radical, which hangs out here, which is where it's most stable, and it adds to another monomer of styrene. And this is called propagation. Eventually, we get to the point where this could be some number of steps, where the radical will recombine with another radical, say from some other chain, or from an initiator fragment, or from some impurity. And this is the termination step. And what you end up with is the polymer. So this is polystyrene. All right. So far, so good. And you can see how this is differentiated from step growth polymerization, because in step growth polymerization, any unreacted A or B functional group can react with any other functional group, either a monomer or another polymer chain, at any time in the process. In a chain growth reaction, only the reactive center, which is the end of the growing chain end, and only one of the growing chain ends, not the other one, because the other end doesn't have a radical, only the growing chain ends are reactive with only other monomers. Incidentally, in general, double bonds, so a double bond is also known as an alkene, are very susceptible to attack by radicals. They have this big fluffy electron cloud above and below the internuclear axis, and they're susceptible to reactivity, and that's why this reacts. The double bonds in the benzene ring don't react in the same way because they are they're aromatic, they're delocalized, and they're very stable and not reactive. Yep.
Fluffy electron cloud, is that what we probably write as pi electrons?
Yes, there's the fluffy electron cloud to which I refer are pi electrons in between the nuclei. Okay, so we have a few choices of radical initiators. One of the ones that you'll see, by the way, this group here is often abbreviated pH for phenyl. Phenyl is just a benzene ring that's attached to something else, and it's abbreviated pH. So this initiator is called dibenzoyl peroxide. And it disassociates under either heat or light to give you two benzoyl radicals, where this bond is susceptible to dissociation, and the two electrons represented by this bond go to either side of the dibenzoyl peroxide, which is abbreviated DBP sometimes in the literature. So we have two of these benzoyl radicals, which decomposes automatically further to two phenyl radicals plus two carbon dioxide molecules, which bubble off. And then in this case, you get two radicals. The pH is R over here. So this is what initiates the reaction. Yep.
Okay. Do you necessarily need to provide more heat for phenyl radicals to detach?
That's a good question. So ordinarily, dibenzoyl peroxide in a lab is kept in a refrigerator. Because it will dissociate at room temperature ultimately, but usually it's raised to 60 or 80 or 100 depending on how fast you want it to initiate. Yep.
What's the squiggly arrow?
Squiggly arrow just means bubbling off. Yep.
Once it degrades into individual benzoyl peroxides, is it spontaneous for it to degrade into phenyl radicals and CO2?
Yes. Yeah, this reaction is very fast. Yeah.
And does that reaction occur just because the oxygen would rather have the electron instead of the phenyl group will donate it over? Or?
It's because of the extraordinary thermodynamic stability of CO2, which is at the root of much of the world's problems right now. Okay, there's another similar type of radical initiator which is used approximately as frequently as DBP. And this is called azo-isobutyryl nitrile. Or isobutyronitrile. which is never called that. It's always called aben. And upon heat or exposure to heat or light, what happens is, well, here, this reaction is driven by the fact that we have this gas ultimately to evolve that's very stable, and this one is too. So what do we have here? We have almost nitrogen gas, which is extraordinarily stable. So what happens here is that one of the electrons from either side of the carbon-nitrogen bond form a third bond in between the nitrogen atoms, and we have two of these nitrile-containing radical initiators plus N2 gas, which again bubbles off. Okay, one more. We can also have a redox reaction. So an oxidation-reduction reaction where we have hydrogen peroxide plus Fe2 plus gives us Fe3 plus OH minus plus the hydroxide radical, which is what initiates the reaction. And with these three mechanisms, we've covered most of the possible radical initiators. You'll have other variations on these themes. For example, to tune the wavelength or the heat at which you need the radical to form. For example, if you have a substrate that is only soluble in a certain solvent, and you need a high temperature dissociation, or maybe you need, maybe your compound is light sensitive, so you have to tune things around a little bit. But this is the general theme. So let's look in a little more detail at initiation and propagation, and we'll just look at polyethylene because it's the easiest. So if we have the phenyl radical derived from dibenzoyl peroxide, which is attacking the an ethylene monomer, we get the phenyl radical, a ethylene group with a radical on it, which attacks another molecule of ethylene. And this, by the way, is called the active center. And ultimately, we end up with polystyrene. By this time, the polystyrene properties are dictated by these repeating CH2 groups, and we never write the initiator fragment unless we're asked to.
Does it typically start with a phenyl radical?
Yes. Honestly, in industry, to make polyethylene, it depends on what on what kind of there are many different kinds of polyethylene. I don't know if it's always. I don't think it's a fair statement to say that it's always done with the phenyl radical. Yeah.
Does the initiator usually affect the chemical property of like the overall polyethylene?
It can, because you can initiate a reaction with something because you know that the initiator fragment is always going to be there. Sometimes you could add a biomolecule to it if you were doing like targeted drug delivery, and that's done actually quite often. So the initiator fragment could actually be another polymer that was made in a previous step. More frequently, and this is something we'll get to on Monday or Wednesday, you might use a specific chain transfer agent that is incorporated into the final product, which again might be tagged in some way or might have some chemical functionality. Okay, what is roughly the time scale? So at typical reaction conditions, polystyrene with a degree of polymerization of 1,000 takes about 1 second, so 1 millisecond per monomer. Ethylene is not the easiest thing to polymerize. In fact, it takes about 2,000 atmospheres at 75 Celsius to get this reaction to go. Okay, how about termination? So the simplest way in which termination can occur is by combination. And this is just two chain ends couple. So the radicals recombine and everybody's happy. No more radicals in the system. And this in one step effectively doubles the average molecular weight. Not really doubles the average molecular weight, but doesn't necessarily double the molecular weight of a given polymer chain, because a 500 mer could couple with 1,000 mer, for example. Yeah.
Clarify, combination, not combination.
You'll pay for that. Yes, combination. This doubles so characteristics are it doubles the molecular weight, and you have two initiator fragments. So spectroscopically, you might be able to tell what was the product of combination. Now, what else could terminate the reaction? Well, you can have another kind of molecular reaction, but one in which the products do not combine, and this is called disproportionation. Disproportionation is a term from chemistry land that means one of your products is the reduced form of the product and the other product is the oxidized form of the product. And the way in which this occurs in radical terminated the termination of radical reactions is as follows. Suppose you have your radical hanging out here, and you have a similar molecule hanging out here. Radicals also like double bonds a lot, but they also have an appetite for hydrogen atoms on CH bonds. So what you can get instead here, instead of combination, is that sometimes you can have what's called a hydrogen atom abstraction. And I promise I will never make you draw any reaction arrows. Most important things to consider here is the kinetic consequences, or the effect of the distribution of molecular weights that you get in either combination or disproportionation. But the end result of this attack on not the end of the growing chain, but the hydrogen atom in the interior to the growing chain, is that you end up with two molecules, one of which is in the reduced state that ends in a methyl group, and the other one is in the oxidized state, which ends in a double bond. And this gives you the hallmarks are one initiator fragment per chain. And you have the predicted molecular weight. So none of this late stage doubling of molecular weight, because we can basically ignore the fact that one of the end groups is a little bit different. Now, we mentioned at the beginning of class that there were different kinds of polyethylene. There was low density polyethylene, which you can get by either having low molecular weight chains, or the other way in which you can get low molecular weight polyethylene or polymers is by branching. So if you have branch structures, it's like having logs in the back of a truck that have no branches and they stack nicely. Or you can have logs where you didn't saw off the branches and the logs are a big mess and they have lots of free volume and they're a lot easier to, move around because they can go volume. So how does the branching occur? Branching occurs in a similar way in which disproportionation occurs by hydrogen atom abstraction, but it happens within the same chain. So this, believe it or not, is called backbiting. Because people that came up with this term did not anticipate sense of humors of people in the 21st century. And this is intramolecular hydrogen abstraction. So let's say we have some polymer chain with a radical at the active center, and I conspicuously draw some hydrogen atom here. And because radicals, sometimes when they can't find anything to react, they'll just react with anything. Particularly juicy hydrogen atoms on another molecule or on their own body. Then what we get is an interior radical, which is the new active center, and now we have a branch. So in a couple more polymerization steps, what we would end up with is something like this with a branch. So this would give you low density polyethylene. So when you look at a particular plastic container and it says LDPE, it's because there was a whole lot of backbiting going on. Yep.
Does the three arrows represent that?
The three arrows represents a bunch of steps that I didn't want to draw explicitly. Okay, production of polyethylene requires extreme conditions. So the extreme conditions are something like 75C, which isn't that extreme, although you wouldn't want to be on a planet that was 75C. But it does require very high pressures. Almost 2,000 atmospheres would be typical. So this is done for polyethylene, but it requires extreme conditions. But you can do a reaction in a lab. If you're not making polyethylene, you're making some other polymer by radical polymerization that go by much, much more mild conditions like atmospheric pressure and just some heating, perhaps under reflux. So this is styrene or vinyl benzene. Nobody calls it vinyl benzene, but it is. But you could if you wanted to. This is vinyl chloride. Anything that's double bond R or double bond X. Let's say X, because R usually refers to something that's made of carbon and hydrogen, whereas X could be anything. This is called vinyl. So anything with a substituent is faster than polyethylene. And the reason is because is more reactive than polyethylene. So it's easier because any substituent stabilizes the radical. All right, let's talk about the kinetics of initiation, propagation, and termination. And this follows a steady state argument. So steady state kinetics, and that means that you assume that the rate of radical formation equals the rate of radical destruction. Rate of radical destruction. So you have initiation, which occurs in two steps, two sub-steps. So our two-step initiation, first we have some generic initiator I. And what it has to do is dissociate by some rate constant Kd into 2 R dots. So you get 2 radical initiators per, you get 2 initiating species per molecule of initiator that you add. And that's true with both the dibenzoyl peroxide and also the azoisobutyryl nitrile, or ABIN. Then you have, so this is decomposition of initiator. And then the second step is the attack on the monomer. Where you have R dot adding to some monomer with some K initiation constant of R M dot. Now, it turns out that the decomposition of the initiator is the rate determining step. So this is the more important term kinetically. Once these are generated, it reacts relatively quickly with the monomers. So this is the slow rate determining step. So what you have for the rate expression, so this is for the rate of thermal initiation. Is some rate v sub I for velocity of initiation equals the rate of appearance of the Rm dot species. So d Rm dot dt equals 2 Kd times F, which is the efficiency by which the radical initiator can propagate chains. So this is 2 because 2 initiators per I. In some cases, like the redox reaction of hydrogen peroxide plus Fe2 plus, you only get 1 initiator per I, so you wouldn't have that there. But in most cases, for thermal decomposition of DBP or ABIN, you would. The F is the efficiency. And the initiator efficiency is the ability of R dot to propagate chains and depending on the system, this is somewhere between 0.3 and 0.8. And it just depends on the idiosyncrasies of the system. So how about propagation? So the propagation reaction is R M sub n dot. So we've added a couple of monomer units plus a monomer unit that just has a 1 because it's just one monomer. Proceeds by some K propagation constant to give you R m sub n plus 1 dot. And your rate expression is Vp is K propagation times the concentration of the monomers times the concentration of the growing chain ends. This is the monomers present in the system at a given time. And this is the concentration of growing chain ends. Also known as active centers. Okay, termination, our last step. By extension, velocity of the termination equals 2 times kT. This is the termination rate constant times 2 of the concentrations of the growing chain ends, and we have a 2 here because 2 radicals are lost for each termination step. And kT subsumes both the rate constants associated with combination or combination and the rate constant associated with termination due to disproportionation. Disproportionation sounds like something against which there should be a federal statute. Okay, the steady state assumption implies that the rate of initiation equals the rate of termination, which gives us 2 kT times the concentration of m dot, the growing chain ends, squared, equals 2 kd, where d is the dissociation rate constant for the dissociation of the initiator, times the times the initiator efficiency times the concentration of the initiator. So what we're going to do to simplify is solve for m dot to give us the square root of f kd times the concentration of the initiator over the termination rate constant kT. But this is too low to measure experimentally, so it's not that useful. And anyway, what we're ultimately interested in is the rate of propagation. Propagation over here can be recast in terms of these variables by way of m dot. We have by substitution is Vp, the rate of propagation, is Kp times the concentration of monomers in the system times the square root of F Kd, concentration of the initiator, over the rate constant of termination. When we return to class on Monday, we will talk about aspects of radical-mediated polymerization. In particular, what we've described so far is applicable principally to uncontrolled polymerization, which is still the vast majority of radical polymerization, but high-value products are generally made by controlled radical polymerization using a couple of techniques that we'll talk about on Monday and Wednesday. Yeah.
So radical is a chain growth process.
Radical is always a chain growth process.